All right, so doing a little review on differential equations, we'll see a differential equations problem in a free response form, and then some differential equation in more of a multiple choice format. So jumping in here. First one, so we're going to look at differential equations in the version of a free response question. First one says, at the beginning of 2010, a landfill contains 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored in the landfill. Planners estimate that W will satisfy the differential equation dW dt, so the derivative of W with respect to time, equals 1 over 25 times the function W minus 300 for the next 20 years. W is measured in tons and T is measured in years starting in 2010. Using the tangent line of the graph at time equals 0 to approximate the solid waste that the landfill contains at the end of the first 3 months. And they do tell us that the first 3 months then would be 1/4 of a year, so at time equals 1/4. So on this one, use the tangent line. So remember, tangent line is going to require two things. One of those things that we need for a tangent line is an ordered pair, and they do tell us that it is at time equals 0. And at time equals 0, which would be at the beginning of 2010, they tell us that we've got 1,400 tons. So it would be 0, 1,400 would be the ordered pair here. And then we need a slope, and our slope's always going to come from our derivative. The derivative that they give us of the function is 1 over 25 W minus 300. And we want to evaluate this at time equals 0. Well, at time equals 0, our function, which is W, has a value of 1,400. So this would actually end up equaling 1 over 25 times 1,400 minus 300. Which ends up giving us a slope here of 44. So that would be 1,400 minus 300 would be 1,100 divided by 25 is 44. So then it says use the tangent line. So if we were to make that into a tangent line here, y minus 1,400 equals our slope times x minus our x value, and we're supposed to use this to estimate what this would be at time equals 1/4. So at time equals 1/4, plugging that in, and I said x, but that's really our independent variable there, t, we'd have y minus 1,400 equals 1/4 minus 0 is 1/4 times 44. So 44 divided by 4 would be 11. Or we would get, adding 11 to that, 1,411 tons. All right, on our next one, part B, it asks us to find the second derivative in terms of W. So they do give us the first derivative. And so taking our second derivative, one of the things that I looked at here, so taking the derivative here, this would be 25, and then 1 over 25W minus whatever 300 divided by 25 is. What would that be here for? 12. But that's just a constant. So as we look at taking the derivative of this, we would get, let me write that out here. The derivative of 1 over 25W would be, well, first of all, power rule, so 1 over 25, but then we would have to take the derivative of W, so times dW dt, which then we would replace with what dW dt equals. So then cleaning that up, we would have 1 over 25 times 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 W minus 300. Why did I replace that? Because it did ask me to write this in terms of W, and right here it would be in terms of the derivative. So I replaced it, so now we have that in terms of W. And I can leave that, or 1 over 25 times 1 over 25. What is that? 1 over 625. Oh, not 625. How about 2500? Let's see here. Where's my eraser? Oops. All right, so then continuing on, it asks us, is that an overestimate or an underestimate? And so then we would consider what we are looking at here. If I were to look at the value here of our second derivative, specifically at time equals 1/4. Well, at time equals 1/4, remember that our function has a value of 1411, so I'm going to replace W with 1411. And the value of this number that I'm getting right here is going to be something positive, which means our second derivative is positive. And so what we're looking at is something that is concave up. And at concave up, then, that means that our function would be an underestimate, because if our function is concave up, the area under that curve would be less than, if I were to show just like rectangles here, you can see that we would have gaps there. We would have an underestimate then for our solid waste. Sticking with that same situation, part C, find the particular solution. W equals W of t to the differential equation dW dt equals. And so what they're giving us is a separable differential equation here. So one thing we could do is separate our variables. I could divide by this term W minus 300. Which then I can integrate both sides. And then they do give us an initial condition. At time equals 0, we got a W value of 1400. And again, that gives us a positive. So I know that if it's 1400, I don't need my absolute value symbols anymore here. Plug in 0 for time. We see that our constant is going to be the natural log of 1100. And then putting that back into my equation here. So I'm going to take this, I'm going to plug it back in here and solve for W. Remember, to solve a natural log, we're going to flip to exponential. Sub W minus 300 equals e raised to the 1/25 t plus natural log of 1100. This natural log of 1100, we're going to see that slide out in front of the e as a coefficient. And then solving for W by adding 300 to both sides. We would have a cleaned up solve for W equation. W equals 1100 e to the 1/25 t plus 300. All right, and then moving into seeing some of this show up in our multiple choice problems, but differential equations. They give us dy dx equals sine x cosine squared. And then they give us some initial conditions. If y equals 0 when x equals pi over 2, what's the value of y when x equals 0? Means I need to find an equation that I can then solve for a second value. So looking at that derivative they gave us, I see that it is a separable differential equation. I get dy equals sine x cosine squared x dx, and I can integrate both sides. Y equals, now here I'm going to use a little u substitution here, and I see that a nice u in this one would be a cosine of x, because its derivative is sine of x, negative sine of x, which is the other function in there. So it will nicely eliminate. So doing my substitution here, I can see that my sine of x's are going to simplify. I'm going to make sure I keep that negative, but we're looking at the integral of u squared. The antiderivative of u squared would be 1/3 u to the third. This did give us an initial condition, so I'm going to go ahead and plug that cosine back in there, and then we'll use our initial conditions to solve. And they told us that y equals 0 when x equals pi over 2. But the cosine of pi over 2 is 0, which raised to the third is still 0, times the negative 1/3 is still 0, so we end up with c equals 0. So again, plugging that back in here, we get y equals negative 1/3 cosine of x raised to the third plus 0. And they ask us to then evaluate this for when x equals 0. Well, cosine of 0 is 1. Raised to the third is still 1. Times a negative 1/3 would be negative 1/3. So going back up to our answer options, that would be option B. All right, on our next one, the general solution of the differential equation x dy equals y dx is a family of, and so I wasn't really sure what to think of this one at first, and so what I just did is I just figured out what the original equations were. So let's start and look at that. First of all, I see that it is a separable differential equation, so I needed to move my y to the left and my x to the right by dividing. Do my integration here. And then solving for y, just to kind of see what we've got going on here, I would have y equals e raised to the natural log of x plus c, which is e raised to the natural log of x, e raised to the c. Well, e raised to the c, that's a constant raised to a constant. That's just a constant. E raised to the natural log of x, remember that if this is the same base, e and natural log are the same base, that we just get an x for that. And e raised to the c is just some constant. So again, I can just represent that as some constant. And so what I get is y equals cx, and so if I compare that to like a linear equation, y equals mx plus b, I can see that the y-intercept is 0. And then we've got some slope, which I don't know what the slope is, it's some variable, but that tells me that it's going to go through our origin with a y-intercept of 0. So this would be a family of lines that pass through the origin. Next one, again, it's kind of asking me what equation could have been the original for dy dt equals ky. And they say that k is some constant in front of that. So again, we see a separable differential equation, meaning I can separate my variables. In doing so, I would divide by y. Integrate, and remember k is some constant. So 1 over y again came from our natural log. K is some constant, so its antiderivative would be kt plus c. And again, figuring out what this could be, if I were to solve this for y, we would have y equals e raised to the kt plus c. Very similarly to what we just talked about on the last page, could be then e to the kt, e to the c. E to the c is just some constant that we could write in front of e as some constant. And so finding the one above that is of that format, that would be option B, 4 being whatever constant they picked, e to the kt. All right, next one, a function that satisfies the equation f times f prime of x equals x, and that f of 0 is 1. So looking at this part right here, that the function times its derivative equals x, instead of f and f prime, I wrote that as y and dy dx. And then I can see that it is a separable differential equation. Just gave me some options here of kind of how to manipulate. So solving then, again, for y, we would integrate, which would give us 1/2 y squared equals 1/2 x squared plus c. They do give us an initial condition that our function equals 1 when x is 0. I'm going to multiply by 2 here for just to get rid of that. And then we can solve for c by plugging in our initial conditions here. Our function equals 1 when x equals 0, which means the constant is 1. Again, plugging that back into our equation, we get y squared equals x squared plus 1. Solving for y, I get y equals x squared plus 1, and comparing that to our options up here, that would be option A. And our last one, just kind of a unique way of looking at a slope field. It says, which of the following differential equations corresponds to the slope field? Notice the numbering goes -2, 0, 2, and then -2, 0, 2. And what they don't have drawn in there is the x and y axis. Your y axis would run right here, and your x axis would run right here. And I just want to show you where those are before I actually draw in there, because once I draw in there, it kind of covers up the little slopes you see. But all the way across our x axis, if I were to draw that line in there, do you see how we would have all of those little slope field lines are horizontal, meaning they have a slope of 0. So all the way across to that line that I just drew in, we have a slope of 0, and that's happening along our x-axis. Well, the thing that is true about every point along our x-axis is that all of those has a y value of 0. And then if we do the same thing down our y-axis, again, before I draw that y-axis in there, you can see every little slope field drawing in there is all a horizontal line. So again, down this axis, we have a slope of 0. And what's true about every point along that line is that all of those have an x value of 0. So as I keep that in mind, as we look at these, the only time that can be true, where we have zeros heading this in our lateral and vertical direction, would be in that top option, because at any other point we would have had undefineds in one of the two directions, whether it's one of B and C when x was 0, all of those should have been undefined, and they weren't. In D and E when y was 0, all of those should have been undefined, and they weren't. And so the only option that works with all of those things is option A, where both x and y are in our numerator. All right, so from here, kind of gives you an idea. Again, you can go back to our section on differential equations and try your differential equations review worksheet, and we'll talk about it at our next Zoom session.